Now, sir, could you please speak? No, sir, not yet.
Yeah. Can you hear me now?
Sir, yes, sir. Now it's perfect.
All right. Okay. So, okay, fine. Yeah. Like that. Cool. No, you can. That's fine. It will be better. Yeah. Yeah. I think it's okay. Now we are on.
Hello, sir.
Hello. Can I be heard?
Yes, I'm good.
Okay, good. And how do I get rid of this right-hand side here?
Video.
You haven't still switched on your camera. It's in the left corner of the Zoom window.
What should I do? Start video or?
Yeah, start video.
Yes. Okay.
Yeah, it's fine. You have a mic. Can you hear, sir? Professor
Yes,
Bhatia?
I can hear you. Yeah.
I'm Nair. Yeah.
Hi, how are you?
Yeah, good. So, yeah, no, not good. No, he can hear. No. Yeah.
So part of my screen is blocked by I'm seeing the lecture hall and
Yes.
and the name Shri Hari Sridharan, etc. So I would like to use my full screen.
No, you can't. Yeah. Yes. Yeah. So, welcome to the first plenary talk, second day of the afternoon of the second day of the conference. So today's speaker is Professor Bhatia from Ashoka University and combined with Indian Subject Institute. So Professor Bhatia is, of course, he doesn't require much introduction for the Indian audience, but perhaps for some of the young researchers, I just say a few words about him. Professor Bhatia did his PhD in the late 1970s. Then he went on to do postdoctoral. Then came back to India, and after a few years stint at PIFR Bombay, in fact, that time I was a graduate student, he just came. Then he moved to Bombay University. He worked there for a few years. Then for the last more than 30 years, he was with ISI Delhi. Then recently, maybe I think 2-3 years ago, he's holding a combined position with Ashoka University in Delhi. So Professor Bhatia is a world leader in the area of matrix analysis. His books on Fourier series and matrix analysis are very popular, and in fact, it has been using. They are being used for many courses. And matrix analysis, especially, is a very good reference to many areas of mathematics. Not only for matrix analysis, including operator theory, and then even in my area on impulse problem and all, while talking about the estimates and all, functions of matrices and all, it's very well referred book. Today he will be speaking on a very interesting topic on matrix analysis and geometry, and then its other aspects like metrics and means on positive definite matrices. Professor Bhatia. Yeah.
Thank you very much for this kind introduction. And I'm very thankful to the organizers to invite me to this meeting. Unfortunately, we can't be all together as we would have in normal times, but I hope there'll be a next time soon. So the chairman has already introduced matrix analysis. I won't say much about it. This talk in particular is about some connections between matrix analysis and Riemannian geometry. And the motivation originally for me was to find good averaging operations on matrices. So I've kept the talk elementary, and it has lots of applications in areas like image processing, radar data, optimal transport, etc. And I hope to explain some of those. It's not moving up, so okay. So one viewpoint from which we can see this is to think of matrices as non-commuting analogs of vector spaces. So Cn, the usual complex Euclidean space with the usual inner product x comma y and the associated norm, the Euclidean norm. Think of n cross n matrices with a corresponding inner product that is trace of A star B and the corresponding norm, the Euclidean norm or the Frobenius norm. The analog of Rn sitting in this space is the space of Hermitian matrices. That's a fruitful viewpoint. The positive vectors, vectors with positive coordinates, now are replaced by positive semi-definite or positive definite matrices. Probability vectors are those whose coordinates add up to 1. Here the analog is you have all positive definite matrices with trace equal to 1. These are called density matrices. Okay, let me summarize quickly some basic facts about positive definite matrices. A is Hermitian, then it's said to be positive semi-definite if the inner product U comma AU is non-negative for all U. If that is strictly positive for all non-zero U, then we say the matrix is positive or positive definite. And I will use the notation A bigger than 0 or A bigger than or equal to 0 for such matrices. Here are some useful characterizations which I'll draw upon. A matrix is positive definite if and only if it's Hermitian and all its eigenvalues are positive. Second characterization, it can be represented as M star for some M. This M is not unique in general. You can replace M by M times a unitary matrix U and still get same A. Then every positive definite matrix has a unique positive definite square root, which I will write as A to the power 1/2. Every positive definite matrix has a unique Hermitian logarithm, which I'll write as log A. And here is the most important characterization. Every positive definite matrix is a Gram matrix or a correlation matrix. By that we mean that you can find n vectors U1, U2, Un such that Aij, the ijth entry of A, is the inner product between Ui and Uj. And that is one reason for the importance of positive definite matrices in areas like statistics, image processing, radar data, etc. So you have n vector valued observations. The correlations between them make up the entries Aij. So the space of data points in many problems is positive definite matrices. There are other problems where the natural space could be the sphere or some other surface. So you see lots of papers these days on manifold valued data or geometry aware algorithms. Essentially, they're exploiting this geometric structure. Again, some basic facts. If you take A and B, positive definite, add them or multiply with positive scalars, you get a positive definite matrix. Most important, if A, B are positive definite, then the product A, B is hardly ever positive definite. By hardly ever, I mean unless A and B commute, which is a trivial case when we study matrices, then A, B is not positive definite. Next fact, take any X. If A is positive definite, then so is X star AX. And I will often restrict to X being non-singular, then such a thing is called a congruence transformation. In particular, and this will be important in my talk, if A and B are positive, then the square root of A times B times square root of A is also positive. So that's the analog of AB is A half, B A half. If A and B are positive, so even though AB is not in general positive, the eigenvalues of AB are positive because these are the eigenvalues of A to the power 1/2, B A to the power 1/2. Then an elementary fact in matrices, if you have a matrix with all eigenvalues positive, then it has a unique square root whose eigenvalues are also positive. I'll denote that square root by AB to the power 1/2. Last thing is very important. I say A is bigger than B if A and B are positive definite and A minus B is positive. So the order on matrices is given by A minus B being positive. This is somewhat deep and subtle, and there is a whole theory of operator monotone functions. So one would imagine that if A is bigger than B, then A square should be bigger than B square. However, that is not the case. In front of you, you see a very elementary 2x2 example. I've written two matrices whose difference is 1, 0, 0, 0. Therefore, A is bigger than B. When you square them up, then the difference is 3, 1, 1, 0, which has negative determinant. So A square is not bigger than B square. So when you see it for the first time, you are surprised that such a basic thing like square function doesn't preserve order. Lohner's theory is about what kinds of functions preserve order. And you define a function on the positive half line to be operator monotone if it preserves this order. Sometimes this is called Lohner's order. So you want, if A is bigger than B, then f of A should be bigger than fb. F is defined by the functional calculus as usual. And Lohner's theorem, one of the deepest theorems in matrix analysis, is F is operator monotone if and only if F has an analytic continuation that maps the upper half plane to the upper half plane. So for this reason, from this theorem in particular, it follows that the tth power function is operator monotone if and only if t is between 0 and 1. So in particular, the square root is a monotone function, but the square is not. Log of x is operator monotone, but the exponential is not. And there is corresponding theory of operator convex functions. I don't need them today. Okay, now the next thing, distances on positive numbers. The usual distance is modulus of A minus B. I'll be talking of two more distances or matrix analogs of two more distances. One of them is, instead of A minus B, I take log A minus log B. Now, all of us are familiar with the logarithmic scale, Richter scale in seismology, decibels in sound, pH values in chemistry. They are all logarithmic scales, so it doesn't have to be justified. Another example which I will study here today is, instead of A minus B, I take square root of A minus square root of B. So there are other metrics of interest. And I want to focus on their matrix analogs. And for that, I want to point out that log A minus log B can also be written as log of A over B. And if I put the modulus, it's the same as log of B over A. This will be important. So if I'm looking for a matrix analog of the logarithmic scale, the first natural candidate is take the norm of log A minus log B. That's interesting and useful, but not so interesting as another distance, which I'm going to define now. Take the same thing, but write it as log of B over A. Then the matrix analog would be log of A to the power minus 1/2 B A to the power minus 1/2. I'm writing it in this way because I need a positive definite matrix to define its logarithm. So if I was to write A inverse B, that is not positive definite, so log may not make sense. So that's why it's written this way. Of course, by the definition of the Euclidean norm, that's just the square root of summation log square eigenvalues of A inverse B. Now, on the face of it, it's not clear that this is a metric, but it is, and it's connected to Riemannian geometry. It has much richer structure than the earlier one I mentioned, and many applications. If A and B commute, then it's just log A minus log B, the true norm of that. So just to break the monotony, here is a quote from Feynman's famous lectures. All the complications of interference, waves, etc. arise because xp minus px is not quite 0. So AB minus BA is not 0. That's why those two distances are different. Okay, a quick recollection of some things we learned in the first course on geometry. Look at a smooth manifold, which I call capital M. For example, the surface of a sphere. Take any point small m on this, then TMM, this thing is the tangent space to the manifold M at the point M. That's the best linear approximation to the manifold. Then at each point M, I have an inner product x comma y in this tangent space TMM. It varies with M. It varies smoothly with M. So that is what is called Riemannian metric in geometry. Not a distance function, but an inner product smoothly varying at with each point. So if I was to take a curve in my manifold, at each point I can look at the tangent vector, which you see here as gamma t is the curve, gamma prime t is the tangent vector. It lies in the tangent space TMM. In each tangent space, I have an inner product which varies with M. So therefore, the norm varies with M. So look at the tangent vector gamma prime t and calculate its norm, the norm depending on the point gamma t. Then the length of gamma is just the integral of the norm of gamma prime t from 0 to 1. So that's how you define the length of a curve in a manifold, Riemannian manifold. In our particular case, I'm looking at positive definite matrices, which are an open set in the space of Hermitian matrices. So locally, the positive definite matrices look like Hermitian matrices. So any 2 points in the tangent space are just Hermitian matrices. The inner product between x and y at the point A. So remember, the inner product varies with the point. Just take it to be a natural trace of A inverse x, A inverse y. So I repeat, positive definite matrices form a manifold. The tangent space at any point A is Hermitian matrices. The inner product between two Hermitian matrices x and y at the point A is given by trace A inverse x, A inverse y. So that's the Riemannian metric. Now, happily, the scalar, the vector version of this was already studied many years ago by Professor C.R. Rao, whose centenary was celebrated last year. So this is the matrix or non-commutative analog of the Fisher-Rao metric. All right, so given any 2 points A and B, take any smooth curve joining them and take its length. Now you ask whether there is a path of minimal length joining A and B. It may not exist, and if it exists, it may not be unique. In this particular case, it can be proved that there is a unique path of minimal length, that's the geodesic. Then you take the length of that geodesic, that gives a distance on the space P. So repeat, delta AB is the length of the geodesic joining A and B. And one has to prove it. There is a geodesic which is unique. Now, a small calculation with matrices or with geometrical ideas shows that this delta AB is exactly the logarithmic distance I wrote earlier. So the log metric is just the Riemannian metric corresponding to this particular definition. So this is called Cartan metric, affine invariant metric, etc. Now, here are some of its important properties. Delta AB is delta A inverse B inverse. If you take congruences, this metric doesn't change. Third one, the exponential map, which is a map from Hermitian matrices into positive definite matrices, increases distances. Now, this has major consequences. So I should just interject here, as an analyst, we feel much more comfortable if we see equations or inequalities. In geometry books, they tend not to write those equations. So I now explicitly want the equation of the curve joining A and B. if one of them is the identity, then it's easy to see that gamma t given by a to the power t. So I am writing the equation of the geodesic joining identity with a. It's easy to see that it's a to the power t. My metric is congruence invariant. So that idea can be used to reduce AB by applying the congruence gamma minus half, where gamma is the congruence by the matrix A. I can get I, a to the power minus half, B, a to the power minus half. Then one of them has become the identity. So the geodesic is just this to the power t. Then undo what I just did, go back. So the natural geodesic joining A and B has this equation: a to the power 1/2, a to the power 1/2 outside, a to the power minus half, b, a to the power minus half, whole thing to the power t. So this is important. Please note this. That's the equation of the geodesic joining A and B. Now this links with something quite wonderful. Many years ago, Fuchs and Voronovich, for problems coming from mathematical physics, defined what they called was a geometric mean of A and B. So I want something like square root of AB, but AB is not positive definite. So square root doesn't make sense. So you can try various things. And it should lead to something nice and have good applications. So this is the definition of the geometric mean. Notice that here I have a positive definite matrix, so it has a positive definite square root. Then again, I'm doing this congruence. Now this is just the midpoint of the geodesic I just wrote down. So I repeat, this is a geometric mean of A and B. The standard notation has been A sharp B. This is just the midpoint of the Riemannian geodesic I wrote. So what is a mean now? So you can demand an averaging function which can be a plus b over 2 or something else. What are the properties you want? You want it to be symmetric. It should be between the minimum and the maximum. It should be homogeneous. It should be monotone. If you increase one of the arguments, then the mean should also increase. It should be continuous, etc. You can put various properties, and all the means you are familiar with have those properties: the arithmetic mean, geometric mean, harmonic mean, and there are many others. Now we want a matrix version, so we could imitate these properties, but you have to modify them accordingly. So for example, the homogeneity is replaced by, I could take just positive numbers and demand the same thing. But more generally, I can demand congruence invariance. If I take A and B and do X star AX to both, then the same thing should be done to the mean. Now this has interpretation in electrical engineering. It's called transformer equation. We may demand the mean should be monotone, but I alerted you that there is a deep theory of Leuner which tells us monotonicity is a tricky issue. There may be requests from other subjects which are applying positive definite matrices. For example, in magnetic resonance imaging, you have a matrix whose 2 by 2 matrix whose determinant represents the volume of water in a tissue. So here is an example of two matrices A and B, both positive definite, both having determinant 1. But if you take determinant of A plus B over 2, you get a number bigger than 1. So when you average the information you get from 2 MRI scans, you get misleading data if you apply the arithmetic mean. You see a swelling which doesn't exist actually. So there is a request that please give us a mean which averages the determinants also. So like that, there are demands from different directions. So if you take the arithmetic mean, you can write immediately A plus B over 2, which makes sense for matrices. If you do with the harmonic mean, you can do the same thing. The geometric mean is problematic because AB is not positive definite. So I cannot take a positive definite square root. So you can try other versions of the geometric mean square root of AB. Some of them work, some of them don't. So this, which I mentioned earlier, Push-Voronovich formula, that has been the accepted correct definition of the geometric mean for a long time. It has other characterizations, which I have written here. I have to push my speed a little bit. This has been very useful. And the problem for a long time had been how to define a good geometric mean of more than 2, even 3, or more than 3 positive definite matrices. The characterizations I have written here do not readily extend to 3 matrices. So what you see here, it's very complicated already to imagine a version for 3 matrices which will have the right properties didn't seem to be possible. So this connection with Riemannian geometry opens up an idea. If the geometric mean of 2 matrices is the midpoint of the geodesic joining those 2 matrices, then it suggests that I can define a mean of M matrices by just taking their center of gravity. So take summation delta square x comma aj, ask for that x where this is minimized. So if you have 2 matrices, this will be just the midpoint of the geodesic. If you have 3, it will be the center of the triangle, and so on. Of course, it has to be proved that such a mean exists, it is unique, and then it should have the right properties. For example, it should be monotone, which I told you is a very difficult, subtle thing in operator theory. And it should meet the demands of applications like elasticity, radar data, and so on. So it's miraculous that it does have all those properties. So what are the properties? I should quickly go through a list. If your matrices are scalars, it's just the usual geometric mean. It should be homogeneous. It should be invariant under permutations. Monotonicity, which I've emphasized already. It should be congruence invariant, etc. So write down all the good properties which a geometric mean should have. So this one has all the right properties: continuity, joint concavity. The determinant of this geometric mean is the geometric mean of the determinants. It is between the harmonic mean and the arithmetic mean. So all the good properties plus many more. So these days, positive unital linear maps, they are called quantum channels. So your mean should have what is called the data processing inequality, which is this one, and so on. So I should emphasize that some of those properties are almost trivial, like symmetry in the variables. Some, like congruence invariance and self-duality, follow from the properties of the metric. And some, like monotonicity and norm inequalities, which is a mixture of operator theory and differential geometry, they are rather difficult. And it has taken 5 or 6 years to prove those. Okay. So the exponential metric inequality, which I mentioned, plays an important role here. I told you, you take the exponential map from the Hermitian matrices to positive definite matrices, then that increases distances. And there is equality here if H and K commute. So the way it is used here is take a triangle in the Euclidean space of Hermitian matrices, take one vertex to be 0, the other two to be H and K. Under the exponential map, it goes to a triangle here. One of the vertices is identity, others are EH and EK. So this EMI tells me this length is bigger than this length, and the other 2 sides of the triangle here are equal to these 2 sides. So that's an important observation. This says that this is a manifold of non-positive curvature, where things are nice. This metric space is complete with this metric, which is useful. It leads to something called the semi-parallelogram law, which I'll skip. A non-positively curved space is a complete metric space whose metric obeys this semi-parallelogram law, also called a Brouillard-Tate space. Now I emphasize that for 2 matrices, there was an explicit formula which I wrote down, the Push-Voronovich formula. For more than 2 matrices, I got it as a solution of a minimization problem. There is no explicit formula. So next best thing is the solution of this equation. So now you need algorithms to compute this. You need some iterative schemes converging to this, which have been found. So I again emphasize there is a good interplay here between differential geometry and matrix analysis. Now, geometers would not have worried about monotonicity, for example. But for matrix analysis or operator theory, that's very important. So to prove monotonicity, people had to imagine algorithms converging to that barycenter, and that in turn gives you a better understanding of the barycenter of these matrices. And in turn, it has lots of applications. I guess I need to skip a little bit. These are algorithms for computing the geometric mean. Okay, because I promised to tell you about two different metrics. So here is the second one. On positive real numbers, take DAB to be the distance between the square root of A and the square root of B. Now, the analog for vectors, positive vectors is obvious. Just take coordinate by coordinate square root and then take the 2 norm. Once again, happy coincidence that Bhattacharya, just a little after C.R. Rao defined his metric, so he gave some analysis with these distances. It's called the Bhattacharya-Hellinger distance and probability. For positive definite matrices, the obvious analog would be to take the norm of square root of A minus square root of B. Just as in the first case, I took log A minus log B, the norm of that. Work this out, you get trace of A plus B minus 2 times square root of A square root of B, and the whole thing raised to the power 1/2. This is interesting, but again, just as in the case of the logarithmic distance, it turns out a much more interesting metric is the one where you replace this A to the power 1/2, B to the power 1/2 by this object, trace of the square root of A half, B A half. So this is called the Bour's distance in quantum information, Wasserstein distance in optimal transport, and it's given by this quantity. So trace of A plus B minus 2 times trace of the square root of A to the power 1/2, B A to the power 1/2, then whole thing under the square root. Now, the first time I was attracted to this is somebody asked me, how do you prove this is a metric? Now, this is, if you bring this 2 here, you have trace of the arithmetic mean minus trace of the geometric mean. So it seems that it should have good properties, but proving that is a different matter. So I will show you why this is a metric and where it's used. So in the beginning, I told you if A is a positive definite matrix, then there exists an M such that A is M star. This M is not unique. So look at the collection of all such M. It's exactly the collection A to the power 1/2, this is the square root of the positive matrix A times U. So there are several matrices here. Call this set F of A, F for fiber. Here is the space of positive definite matrices. Over A is sitting this fiber F of A, and over B is sitting this fiber F of B. And ask the question, what is the distance between these two fibers? That's the minimum of M minus N, where M varies in F of A and N varies in F of B. In other words, this is the minimum of A to the power 1/2 minus B to the power 1/2 U. Now, this is a classical problem in statistics called the Procrustes problem, first studied in psychometry, factor analysis. You want to determine when two data sets are the same. Data sets here mean N by N positive matrices. They may be the same up to a rotation. So from different angles, they look different, but essentially one is the rotation of the other. So you want to look at A minus BU. Second thing, they may be nearly the same, not exactly the same. So up to a rotation, they are nearly the same. So you want to minimize this A minus BU over all unitary U. And that is a well-studied problem, quite elementary. The answer is the minimum is attained at that U, which occurs in the polar decomposition of B star A. So look at the polar decomposition of B star A, which is U times the absolute value of B star A, which means square root of this matrix. So that answer is known. So plug that in here and you see that distance, that DAB, which I wrote down, that complicated thing with traces, is nothing but the distance between the fibers FA and FB, which is the minimum of A to the power 1/2 minus B half U. And that in particular proves that D is a metric. So that's elementary matrix analysis. This quantity trace of the square root of a to the power 1/2 be a to the power 1/2 is called the fidelity between the states A and B. So if A and B are density matrices, then this is called the fidelity. So A and B are positive definite matrices of trace 1. Pure states are those which come from vectors. So take unit vectors u and v. If A is u star, B is v star, then these are called pure states. In this case, you can see fidelity between A and B is just absolute value of the inner product between them. So it's kind of correlation, and this is generalization to n cross n matrices. So this distance is important in various areas. Now, fidelity is an important quantity, so people try to find characterizations for that. So one of them is put A and B on the diagonal, put M in the corner, M star, and ask for an M whose trace is the maximum subject to the constraint that this matrix is positive definite. So I repeat, A and B on the diagonal, M star here, ask for this matrix to be positive. Among them, look for that M which has the maximum trace, that's the fidelity. This is a useful thing. Now I explain quickly the relation between this distance and the optimal transport problem. So that's an important area these days. So imagine you have the furniture lying in this lecture room and you want to shift it to some other arrangement at minimum cost. So this distribution on the floor, let's say, is a probability distribution, a probability measure on R2, and you want to lift it and take it somewhere else. So general problem is you have two probability measures, mu and nu on Rn. And imagine there is a cost of moving something from point X to Y. And look at all product measures on Rn cross Rn whose marginals, that means whose projections are mu and nu. And you want to minimize this. So that's the optimal transport problem. How to shift material from one configuration to another while minimizing the cost. Then there are general theorems which tell you under some conditions on the measures, it has to be regular and so on. And some conditions on the cost function, there are unique solutions. In particular, if you take the cost function to be x minus y square, then this is called the Wasserstein distance between the measures mu and nu. So what has this got to do with matrices? One of the most interesting special cases is the case of what are called Gaussian distributions. Take two vectors x and y, think of them as random vectors. And this wiggle means x is normal distribution with mean 0 and covariance matrix A. By that I mean that this matrix A is the covariance matrix of x. By that we mean in turn that the ijth entry of A is the expectation of xi bar xj. Similarly, the covariance matrix of y is B, which means the expectation of I bar yj is the ijth entry of B. The problem I just told you in this special case is to find the minimum of the expectation of norm x minus y square, minimum subject to the constraint that x varies, x has covariance matrix A and y has covariance matrix B. So put that as the constraint and ask for minimizing of this function. Now, using the properties of fidelities, etc., which I will not go through, just this is a simple calculation. You can see that that metric D square AB, square of the metric DAB, which I wrote earlier, is just the solution to this minimization problem. That gives another proof that this is a metric, by the way. Then a little more of calculation shows that the solution to the optimal transport problem is that x should be taken to Tx, where T is the geometric mean of A inverse and B. This is the geometric mean which we were talking of in the first part of the talk. So that reappears here. So that's called the optimal transport plan in shifting the material. So I hope I have conveyed some flavor of this. Okay. So now, because of our success with the first problem, linking it with Riemannian geometry, one may ask, does this metric also arise from a Riemannian geometry consideration. I wrote down the definition of the metric. Remember that trace of the arithmetic mean minus trace of the geometric mean, whole thing raised to the square root. Does it arise from a Riemannian geometry situation? And the answer is yes. So there are general theorems, but this we have to work backwards. In the first case, I could write a natural Riemannian metric and calculate the distance function corresponding to that, and I got my logarithmic distance. Here I have a distance given to me by the optimal transport literature, and I want to see whether it arises from Riemannian geometry. And the answer is yes. I will not go into this. The inner product is not so nice and natural as we wrote in the first case, but you can write it explicitly. In turn, this is related to solutions of the Sylvester equation in matrix theory and so on. So the theme of my talk is how to apply ideas coming from matrix analysis to these problems in geometry and applications. So here are the difficulties with this metric. There are fewer isometries than we had in the first case. The metric space is now not complete. Inequalities like exponential metric increasing property, semi-parallelogram law are not available. That was a manifold of negative curvature or non-positive curvature. This is a manifold of positive curvature, but still you could do nice things with this. So as I said, analysts feel much more comfortable if they see inequalities or equations. So first problem, can I explicitly write down the geodesic equation of the geodesic joining A and B in this metric? The answer is yes, you can do that. The length of this geodesic is exactly the distance function we started with. The midpoint is given by this. So if these were numbers, this is just the average of the arithmetic mean and the geometric mean. So if I was to do it ab initio, you may think this guy is being silly, just why go on taking averages of averages and so on. But it's quite natural here. So it's the average of the arithmetic mean and the geometric mean, the non-commutative version, and that just turns out to be the midpoint of the geodesic joining A and B in this Riemannian metric. All right, again, I'll skip this one. Okay, then there is once you have it, then as we did for the Cartan metric, I may also look for the mean of several positive definite matrices. And that is finding the barycenter of A1, A2, AM with respect to this. This is studied as multi-marginal optimal transport problem, which is introduced in the economics literature to begin with, an N coupling problem. We have obtained proofs using matrix analysis of some of their theorems, which are more natural. So let me end with that. So I have to solve this minimization problem. One has to prove it has a unique solution. That's the Wasserstein barycenter. That's also the solution of this. Okay, so you can tell what is the optimal transport plan. That is the M variable version of the first problem. So you have something lying here, which you have to take to M-1 different points with the least cost. So once again, minimization of an integral. The Gaussian case is exactly what we have said here. So last comment, this D square AB, as I said, was trace of A plus B over 2 minus trace of the square root of A half B A half. Now this is the arithmetic mean, no ambiguity. I know arithmetic mean should be A plus B over 2. This is a geometric mean. And in the first part of my talk, I pushed the view that the natural geometric mean is A sharp B, not this object, for other reasons. So it would have been more natural to put this geometric mean here rather than this. So look at trace of A plus B over 2 minus trace of A sharp B. But that's what we would have wished. It turns out that this is not a metric. So God doesn't will this to be a metric, though this is the arithmetic mean, this is the geometric mean, but it doesn't happen to be a metric. Triangle inequality is violated. However, it's still a good idea to chase. This is what turns out to be a divergence. It has some of the nice properties of distances. So thank you very much for listening to this. I haven't made a list of all the literature, but the first problem I talked about, you can find in this book. Then this is growing as a subject called matrix information geometry. There are books on this now. So some articles on this problem you can find in this book. And we have written an expository article on the second metric, Bose-Wasserstein distance, which appeared 2 years ago. Thank you. Mr. Chairman, I have finished.
Yeah, please. No, it's, oh, it's muted. Yeah, thank you, Professor Bhatia, for a very interesting exposition on various aspects of positive definite matrices and its connection with the geometry, metrics, and then many, even perturbation results and inequalities. So, any question from the audience? Any question from the audience in the online? Yeah, there is some. Yeah, Professor Bhatia, how does the completion look like P under D? That's what the one question in the audience. It's not listening. Professor Bhatia, can you hear?
Yes, I can hear you, but at the moment I don't have the answer with me. That's
Okay.
a good question.
Yeah.
A natural thing would be to see that the positive semi-definite matrices should constitute the completion, but I'll have to think how to prove that.
Okay. Yeah. Any question from the audience here? Yeah, in fact, so anyway, I have some remark only. The powers of operators, positive definite operators, and the logarithm of, in general, positive definite operators on Hilbert spaces are also very important in smoothing powers of operators. So do you think that these will have the corresponding analog, some of the results here in the operator setting also?
If you want to define this for infinite dimensions, then I wrote down an equation. See, in the infinite dimensions, that Riemannian geometry structure is not there.
Okay.
But I wrote an equation which the first mean, by the way, is called Karcher mean. For some reason, Karcher is not happy with that. But whatever it is, I wrote down an equation in terms of logarithms. So if you remember, I said for more than two matrices, there is no explicit formula.
Okay.
But the mean is the solution of non-linear matrix equation, which was in terms of logarithms. Now that makes sense in infinite dimensions. So for infinite dimensional operators, or even in C-star algebras, the very definition of the mean is that solution of that equation.
For that, you mean the Riccati equation?
No, not Riccati.
Okay.
I'll have to go back if you like.
That's okay. It's okay.
It was a logarithmic equation, summation log x to the power minus half aj x to the power minus half is equal to 0.
Hmm.
So that's called the Karcher equation, though it was written by Cartan. So that makes sense for infinite dimensional operators for C-star algebras, though there is no natural Riemannian geometry there. So that is the definition of the geometric mean of several variables. And of course, it's easy to define, but then you have to prove it has the right properties and it has uses, which has been done recently.
Okay. Okay. There is I think there is a question. One remark, I think. Many thanks for the interesting talk. You mentioned that there were good numerical methods for computing the geometric mean under the first metric that you discussed. Is the same true for the second metric?
Second metric, there are papers, though I think it's less developed than the first one. So look at the last reference you see on the screen.
Okay.
There you will see a reference to that paper. There are 4 authors from Spain who wrote a paper giving convergence method to lead to the mean, but it's less developed than the first one. But there are some results there. So in this paper, you will see a reference.
Okay.
Not just a reference, the last article explains the idea also.
Okay, okay. So there is another question. Is the manifold P an algebraic variety?
It's defined by inequalities rather than, so you need equations to define varieties. These are inequalities. So
Yeah, I think, it's not immediate as a question. Okay, I think there is no further question from the online. So if there is no other question from here, let us thank Professor Bhatia for a very, very interesting talk. Thank you.
thank you very much. Thank you.